We're living in a world of big data, and the question is, what's next? And first of all, what should we do with all these big data? Well, solving problems, of course. Well, they're all problems like external threats to society, like hurricanes, volcano outbreaks, and many other natural disasters. But the modern problems are of a different nature. They're societal and economic problems. They're based on systemic instabilities such as financial and economic crisis, social political instabilities, environmental and climate change, or also crime, cybercrime, spreading of emerging diseases. Ebola is just one example for this. So we must realize that we are living in a new, complex world. In fact, people like Sandy Pentland have voiced quite clearly our financial, transportation, and health system are broken. And also, the former president of the Santa Fe Institute finds that actually we are seeing a failure of our current systems. In fact, these problems are extremely expensive to our society, so we pay billions, if not trillions, in order to fix these problems. On the other hand, if you could just improve these problems by 1%, not even to talk about 10 to 30%, which I think is possible, then we could really save a lot of money, and on the other hand, we can make a lot of money with new kinds of business ideas. Now, how would we do this? Well, we need complexity science for this. It can tell us how to create a better world. But what are the problems in the first place? One of the problems is unstable dynamics in complex systems. So have a look at this. Under normal conditions, pedestrians organize quite smoothly into these lanes of uniform walking direction. And that creates an efficient flow, some self-organized order, as if there was Adam Smith's invisible hand actually taking care of this. However, we know that if the density is too large, then things can get out of control and crowd disasters can happen. So even if nobody wants to harm anybody, it could happen that hundreds of people die. How to understand these kinds of problems? Well, let's take this example. It doesn't seem to be difficult to drive in a circle, but we will witness in a few seconds actually the breakdown of traffic flow. A so-called phantom traffic jam has now formed. You can see it moving backward. And you won't get rid of this phantom traffic jam anymore. So, what's the reason for this? If you would talk to a driver, it would probably say, hey, there was a stupid driver in front of me who didn't know how to drive a car. But there is a physics that allows us to understand this kind of phenomena. And the formulas behind this physics tell us that there is a critical density above which the slightest variations actually will be amplified. So if one car varies in speed, then the next one will have to respond, but that happens with a delay. In order to compensate for the delay, we'll press the brake a little bit harder, and the next one even harder, and so on. So there is a cascade effect, a domino effect, and finally people get stopped, although nobody wants this to happen. Now this is actually a prime example for systemic instability, where everyone is well educated, has a good training, good technology, all the information that it seems to take, and the very best intentions. But sooner or later things get out of control. Now there are other systems where these kind of effect happens, in particular in complex networks, where a single failure can actually trigger many failures. And here is an experiment to illustrate that, where one single local perturbation is actually messing up the entire system within a very short time. Now, this experiment has been designed to illustrate chain reactions, as we know now actually from nuclear fission. And we know these kind of processes can be controlled, but it's difficult to control them. And sometimes they're getting out of control, as we've seen in Chernobyl and in Fukushima, for example. And in fact, there are other examples, such as in the financial system, where we've seen that bankruptcies of banks have caused further bankruptcies. And this video illustrates that within a couple of months, actually hundreds of banks go bankrupt, and it causes losses of hundreds of billions. So this looks pretty much like the experiment we've seen before, and obviously this is not a desirable effect. Well, things are actually even more serious than that, because today we have networks of networks, and they come with complex interdependencies. This is actually the risk interdependency map that the World Economic Forum has created, and it shows you that actually the greatest risks today are of social or economic nature. So we certainly need to understand them. We need to be able to fix them. So fortunately, now we have way more data than we had ever before. Can we fix these problems with these kinds of data? And if so, how? Well, it seems that with a growing amount of data, we could actually one day know everything on Earth. And that inspires basically the idea one could build a giant crystal ball to forecast the future. Now, with all this information, could we act like a wise king, like a benevolent dictator, who would basically optimize the state of the world, create the best worlds that we could imagine? Would that be possible in principle with all these data? Well, it would certainly need tools also to influence the future, and given that knowledge is power, you could think that it might be possible to create something like a magic wand that's going to change the future as you like it, and manipulating people's decisions. However, it turns out there are limitations. So big data is not a universal solution. And this can be seen with this graph over here. So have a look at the blue curve first. So that shows processing power as it grows over time exponentially. Every 18 months it's doubling. But data volume shown in green is actually doubling much faster. That means every 12 months. So what we see is that we're getting from a situation where we didn't have enough data to take the decisions into a situation where big data allows us to take evidence-based decisions. However, you can see on the right-hand side that there is a growing gap between data volume and processing power. And that has serious implications, because that means there will be something like dark data, data that you will never be able to process, never be able to touch and understand. And that gap is becoming greater and greater. So what does it mean? It basically means that we would most likely focus on a number of problems while overlooking some other problems that are around the corner. And this seems to be happening already, actually. Most people didn't see the financial crisis coming. Most people didn't see the ISIS fighters coming. So these things happen all the time, and we seem to be already on the right-hand side of this graph. Here's another example. Google's New Trends was often advocated as a big success story of big data. However, it has recently been criticized for not being accurate, not being reliable. And so the question is, are there better methods than that? In fact, they are. So have a look at this. This shows basically data from the World Health Organization. And if you look at that in a spatial-temporal way, how an epidemic spreads, then it looks pretty chaotic. So it doesn't seem to make sense how the epidemic spreads over the world. And you can see this unsystematic spreading in the clouds of points over there, so there's no clear structure there. However, there is actually some information that we can use, which is the travel volumes of people traveling between the airports. And using this information, we can define a new effective distance. So combining the few data from the World Health Organization with the travel volume data allows us to transform the problem into another one, which has these linear interdependencies and therefore implies predictability. In fact, what we can do is map this whole spreading process into a circular process. And that means that if we look at infection data from all the airports in the world, we can identify the most circular pattern. This most circular pattern identifies the most likely outbreak location, which is often not known at the beginning. Now, given the identification of the outbreak location and the circular spreading pattern, we can also calculate into the future. So we can basically say what are the cities that are likely to be hit next by the epidemics. So we do have a predictive model over here. So what I'm saying here is we're not witnessing the end of theory. On the contrary, what we need to do is combine data with models in order to have much deeper insights, much better predictions. Now, have a look at the red curve. This is systemic complexity, which increases as we go on networking the world. And this is actually exploding even much faster than data volumes. So what it means is basically, it's likely that we'll lose top-down control. The complexity of the world will be so big and is already so big that we cannot optimize these systems in real time. And given the large variability, we cannot do it offline. So basically, we're not able to come up with the best solution in a top-down way. So
what's the reason for that being factorial?
Because of the number of possibilities to combine different objects with each other as you network them to create new objects. And I'll give you some evidence for this being true. So what is the solution? Do we have another option apart from top-down regulation? Well, in fact, this is distributed control. This is self-regulation. The rest of my talk is basically on this. So what it means is, as the level of complexity increases, we have to increase the level of autonomy of the system elements in order to be able to achieve our goal. And let me illustrate that a little bit with a paradigm shift. So in disaster response management, people had pretty much a military kind of organization in the past. So there was a guy on top, a woman, basically saying what everybody had to do. And those people had other subordinates and were telling them what to do. Now, we just had actually a hackathon in San Francisco about earthquake resilience. And what the hack teams came up with was something very different and very convincing. They had created information platforms that were basically combining top-down with bottom-up. So the idea is that the government, say, would announce, okay, we need that much water, we need that much food of this kind, we need fuel here, and we need clothes over there. And then companies and people who are willing to help would sign up and say, I can do this, I can do that, I can contribute this. And this is something which is creating a much more efficient way of managing these kind of systems. Now, imagine that most of our systems are changing much more quickly these days. So, in some sense, policy making and also business becomes a little bit like disaster management. There are always some problems that need to be fought, and so it's pretty much this kind of situation that we need to be more flexible and more efficient in addressing these kind of problems. So I predict a paradigm shift. And actually, we can already see this trend towards decentralized bottom-up approaches because it's more efficient. Take Bitcoin, for example. It's a peer-to-peer money, and it became even more valuable than gold. Or take peer-to-peer lending, or Uber taxis, or intelligence walls. And also in traffic control, actually, we are seeing a trend towards decentralized strategies such as car-to-car communication. Now, the dream to create self-regulating systems, and actually a self-regulating society, is about 300 years old. Actually, this book from 1714, The Fable of the Bees, was formulating this idea that if everyone is just doing what's best for him or herself, would basically create a beneficial outcome. And we know this principle as the principle of the invisible hand from Adam Smith. And so why couldn't society work pretty much like this, so very much coordinated and ordered automatically? Well, unfortunately, sometimes the invisible hand works, but in many cases we've also seen it fail. So environmental pollution is one example, or overfishing, or climate change. So all of these problems are so-called public goods problems, or social dilemma situation. And the situations like this, that cooperation of everyone would be favorable in principle for everyone. But there is a temptation basically to make a smaller contribution, get out more from the system, and that destabilizes the desirable state, which means that cooperation erodes and we end up with a tragedy of the commons. It's pretty much similar to the situation where we had free traffic flow, which was a desirable state, but it broke down because it was unstable. So the question is, can we overcome traffic congestion? Can we overcome tragedies of the commons? And the classical approach is, we have these kind of world meetings and try to come up with regulations for the world. But as you know, for many years negotiations have been going on and there is no conclusion yet. What I'm now claiming is that 300 years later, after the book that I've just shown you, by combining complexity science and real-time feedback enabled by the Internet of Things, we can now create self-regulating systems and finally make the invisible hand work. So the Internet of Things is the enabling technology, and it's pretty much feasible to do all of this based on local interactions. So to give an example, let us first look at this annoying stop-and-go traffic over here, and then later on show how technology can overcome this congestion. So in order to see actually what's the problem here, I'll turn this car into a helicopter. I'd love to have such a car as well, I bet. And we'll be able to see what's actually the reason for this annoying traffic jam. And it turns out it's the cars over there that come in through the on-ramp that are producing small perturbations, and these perturbations are basically adding up. There's an amplification and a chain reaction and causes stopping the traffic. Now, assume we equip these cars with radar sensors that would measure distance and relative velocity and would drive the cars automatically. That's work that we did in 2007 and before. It turns out that by slightly changing the parameters of driving, that means by changing the interactions between the cars, we can get rid of the traffic jams, even though the inflow stays absolutely the same. So, with real-time data and adaptive feedback, we can fix the problem. I'll give you another example for why self-regulation is resource efficient. And for this, we're comparing traffic light control systems. This is basically what we have today. So we have a central traffic control authority with a computer center that's collecting data from all over the city. It's trying to optimize traffic flow. And once it has figured out how to do that, basically distributes commands to the traffic lights. So it's pretty much this concept of the benevolent dictator. The problem is that traffic optimization is actually an NP-hard problem That means you cannot really do that in real time, not even with a supercomputer. And so you have to do simplifications, and you're throwing away many good solutions. Our approach was very different. We said, okay, given that traffic flow is so variable, so unpredictable, the right answer is neither planning nor optimization, but it's flexible response to local conditions. And so let's look basically in two approaches to respond flexibly to the local conditions. One is that every intersection strictly tries to minimize travel times. You could say the Homo economicus would do exactly this. He would try to do the optimal job where he is actually deciding. Okay? Now, this one is doing exactly the same, but taking care of traffic jams that are growing so big that they might actually reach the neighboring intersection. And let's see what happens if, in such kind of situations, this queue is first cleared before it goes back again to minimization of travel times. So, what we see over here is the queue length that results as a function of the capacity utilization. And have a look at the red code first. So that's the top-down regulation. Clearly, as the capacity utilization of the intersection increases, the queue length increases as well. And that's expected somehow. So how well is actually the selfish optimization doing? The Homo economicus, as I say. Much better. Much, much better. So much shorter queue length. But hey, what's happening here? So suddenly there is an explosion of the queue lengths, and we can say that over here Adam Smith's invisible hand works, and on the right, unfortunately, it fails. So if we push the selfish optimization too much, then the self-organized coordination breaks down and fails. As we've also seen it basically in the financial meltdown. So the question is then, how is it if we pay attention to what might happen to the neighboring intersections while also trying to minimize travel times? Well, as you see, the blue curve shows that this is actually superior to both previous approaches, all over the way. So, interestingly enough, bottom-up self-regulation can outsmart optimal top-down control attempts. And we get these beautiful green waves as a result of this local coordination that results from self-organization, and the local coordination actually spreads all over the city by self-organization. And this is really very interesting, because we are now using the internal forces of the system in order to reach the outcome that we'd like to have. The principle has been inspired, by the way, by pedestrian flows, where we found that there are oscillations in the walking direction and bottlenecks. So it looks like there was a traffic light, but there's of course no traffic light over there. So basically what we're doing is we're transferring the pressure principle that we have identified as the cause of these oscillations from the pedestrian example to the traffic flow, and those self-organized oscillations define our traffic light. So what happens now is the traffic flows control the traffic lights rather than the other way around. Works much better, as you can see. So, great reduction for public transport in terms of the waiting times. Even an improvement also for individualized traffic, and for pedestrian cyclists is good as well. And the environment too. So, this is really something quite unexpected, and it means it's a very powerful new principle. So self-organization and self-regulation are approaches which can master the complexity of today's systems and benefit from it. And it means to go from such a situation where we're trying to regulate every single detail of our decisions and actions by something which is an infrastructure or institution that would basically support us in our decisions and support us in taking effective actions. And here is actually a funny example of a particular site that work surprisingly well without any traffic lights. And you will almost never see anybody stop over here. So what's the reason for this? Well, it's a particular design. So we have a unidirectional traffic flow in front and unidirectional traffic flow in the opposite direction in the back, and in between a buffer which allows people to adjust their speed such that they would find a gap just for them when they arrive. So this is a simple trick, and as I said, it requires the right kind of design. So suitable interaction mechanisms, that's the question. Could we transfer them from technological systems also to the entirety of our economy and our society? Could we create a self-regulating economy and a self-regulating society? And in fact, Nobel Prize winner Elinor Ostrom has shown empirically that self-government is actually efficient, given proper design principles. So, what would we need to do? Well, let's look at situations where two people or two companies interact with each other. So in principle, then we can have 4 different kinds of situations. We could have a lose-lose situation. The interaction wouldn't be good for any of these interaction partners. In this situation, of course, we should avoid this interaction in the first place. We could have a win-win situation, so it's good for both sides, and then we should engage in the interaction. We could perhaps decide that we want to improve fairness in the outcomes, so that would require some value transfer. There could also be a bad win-lose situation, so basically one would win, the other would lose, but in sum it would be bad. And as one of them would win, the other one would have to be protected from this interaction. And good win-lose situations are those situations where one wins, the other loses, but overall the outcome is positive. So a value transfer would make it attractive to interact for both sides, actually. And that implies that we can actually create a number of social information technologies that could help us to master this kind of situations better. So what I call the social mirror could actually support us in getting a better picture of the situation we're actually in. What are win-win situations, what are win-lose situations, and so on. The social adapter, intercultural adapter as I call it, would support us in engaging in profitable interactions. Social protector would help us to avoid lossful interactions, and finally social money would be there to enable this value transfer. So the idea of the social mirror is basically that we get a better picture of what are the implications of our decisions and actions. So what is our social or economic or environmental footprint, basically? What are the externalities that we produce? And so we could think of creating something like environmental maps and ecosystem maps. It means to map change and who is causing it. Or we could create resource maps where we're mapping resources and who uses them. Or we could also create actually financial observatories such as the ESNet has created it. We could also map social capital to protect it. And what is social capital? It's actually something which is important to create economic value and also social well-being. So things like reputation, trust, solidarity, compliance, and other things that are important. And by the way, happiness as well. We could also map conflict, tensions and how they come about. And that is actually quite insightful because then there are much less surprises about the wars that are finally resulting. And we could actually map culture and how it spreads. And surprisingly, we know pretty little about how culture works in detail. What are the success principles of all the cultures in the world? what are these self-regulating systems that are built on. So if we would understand that much better, we could come up with something like a translator for different cultures. It would be like having a guide who explains us how other people think, what are they interested in, and how could we engage in a profitable interaction. So there would be much less missed opportunities. Now, data will allow us to actually create completely new instruments to explore and improve the world. And Future ICT had a number of proposals in this connection. It said we could actually create a learned nervous system, which is actually a system which would measure in real time what's going on in the world. And this way enable real-time feedback. This kind of data could be actually fed into interactive virtual worlds. And these would allow us to explore particular rule sets and in this way basically see what would happen if we implement a new law or a new rule. And there would be reputation systems in order to have a reward system and also a quality insurance mechanism, and finally participatory platforms for crowdsourcing, co-creation, and self-regulation. So let me go a little bit more into this. The idea of the learned nervous system has actually been taken up, so you probably know this book about the human phase of big data, and the foreword actually has exactly this title. And so how would it work? Well, we could actually use a lot of data which is already out there on the web, such as figure photographs. As you can see, there are actually hundreds of these photographs about the Colosseum in Rome. And if you put this information together, you can actually make a 3D reconstruction from your desk at home. And this can be done actually from any place in the world which people are taking in their photographs. We can also map scientific productivity, impact and flow of ideas, knowledge production and consumption, and also the concepts in physics and other kinds of sciences. We can identify new trends early on and all these kind of things. So these things are now becoming much more available and understandable. So what would we do with this kind of data? Well, we could feed them in simulators and would allow us to understand these annoying traffic jams. So there are actually astonishingly many different traffic patterns, and all of them can be simulated. They correspond actually to the empirical data very well, and we can also come up, of course, with models of power failures, of conflict spreading, as we've studied it for Jerusalem, and also to look into supply chains and their resilience, as we have done it recently for the European gas supply network. So these are just some examples, and so the idea is that we could basically put together all those models. As I said, models are superior to just data mining and machine learning if you combine these models with data. So we could combine traffic production and economic models, models of crowd behavior, social cooperation, social norms, social conflict, crime, war, and whatever, and then scale it up to global scale, and eventually increase the degree of detail and accuracy, as we've done that for weather forecasts in the past. But besides creating a mirror world, we can actually establish interactive virtual worlds to explore new socioeconomic mechanisms. So in a sense, we could create parallel worlds with different financial architectures, different decision-making rules, different intellectual property right regimes, and all these kind of things. And, you know, every one of us could spend some time there and enjoy those roles that we really like most. And among those mechanisms checked out over there, we could then implement some of them in our real life. And in fact, it's going there already, so we're building interactive games as experimental platforms, in order to get towards a high throughput experimenting in the social sciences, to get a breakthrough, an explosion of understanding, as we have seen it actually in the Human Genome Project before. So that was the explosion. So, back on track. Now, the reputation systems, what are they good for? Actually, reputation systems can provide institutional frameworks to overcome tragedies of the commons. And they're basically the mechanisms to, analogous, one could say, to the traffic assistance system. So, astonishingly enough, they're good for both sides, for consumers and producers. So consumers get a better service, and producers can sell it at a higher price. So it's basically rewarding good behavior. And however, we need to have better reputation system than today. What we need to have is a reputation system that protect social diversity and that are pluralistic, so we need to have multi-criteria reputation system, because otherwise it can undermine the wisdom of crowds and we will end up living in filter bubbles, and we don't want this to happen. And finally, we would like to have multidimensional money, because that would establish a reward system to support self-regulation. And in fact, I think it would also help to overcome the financial crisis that we used to have since hundreds of years. So finally, why do we need participatory platforms? Well, that follows basically from the need to move towards a more distributed control and decentralized management of increasingly complex systems. And what does it mean? Well, basically, we need to create systems that enable people to take good decisions. We need to create options and opportunities. And in fact, in a sense, these systems are coming up. Social media are pretty much along these lines. It's probably one of the reasons why they're so successful. And we're seeing that now consumers are actually becoming much more important. Consumption is not just becoming more user-centric, but also consumers are making active contributions actually to production. So we talk about co-creation here, and that will become much more important. Also through new technologies such as 3D printing, for example. So I'm concluding with saying that we need a joint global effort to master global 21st century challenges and to build a participatory framework for the emerging digital society. So how to do that together, and what would be the features? Well, first of all, the system should be a trustful system. And that requires transparency on the one hand. It also requires a suitable concept for privacy protection and data ownership. And it's eventually coming up, and it needs to give much more opportunities to users to work with data. We are pretty much restricted today in the way we're using data. So, for example, we have created this virtual journal where everyone can come up with a number of different information filters. So I could say, okay, show me the most recent papers in this field. Or show me the most controversial papers, or show me the papers that my most admired colleague is reading, or show me some surprise papers, whatever. So I could then share these filters with my friends and colleagues. They could modify them, and in this way, basically, an information ecosystem would be created. So sharing is very important, and just imagine that everyone would own 100 words, and whenever you wanted to use any other words, you would have to pay for it. Now, that wouldn't be very efficient to talk to each other, right? So, language and culture pretty much based on sharing, and so this is a very important principle. And so, how to build a system that would have all these features? I think the best way of doing this is to create an Internet of Things as a citizen web, where basically the citizens are building the components of the web. They would be connected with each other, but the citizens would be very much in control of the data generation and data sharing, and so it would be a trustful system and a transparent system. And this system, that's my proposal basically, to build that together. So many people would make a contribution in the spirit of open source, would create, in a sense, collective intelligence by bringing so many great ideas together. And not only this, it would actually create an entire information and innovation ecosystem where everyone could use these data. That means politics, business, science, and the citizens. So everyone would benefit from these data, and everyone could use it to run their own businesses on top of this. So, you could make money with it. You would make money not with the data, but with the algorithms to turn data from data into information, from information into knowledge, and from knowledge into wisdom. And we have started actually to create a system. So this is my team of students who's working on creating this planetary nervous system as an open participatory system. And very much in the spirit of the maker community. And so the hope is that over time, it would grow beyond Zurich and eventually, reach all over the planet. So it would really become a planetary nervous system. And I'd like to invite you today to participate in this endeavor. Thank you very much.